Topic 2, Part 3, the Lagrange multiplier trick, or in other words, constrained mathematical programming. So far, when we've been looking at two variable problems, we've just looked at an objective function, and we've found ways of taking the objective function and using things like contour plots and 3D plots. Then we've found the stationary point, okay, and we've been able to take those stationary points and say something about whether they're a maximum, and say something about whether they're a maximum. We're now going to add in one or more constraints, and so it's going to say that this objective function is maximized subject to some constraints, and the first constraint is that x1 minus x2 plus 10 is equal to 0, and then we've got some other constraints in there which are called non-negativities. They're just making sure that x1 and x2 are greater than or equal to 0. Let's just take this constraint here. It's written in a slightly strange way, but it can be interpreted in a common sense way. So it's saying that x1 plus x2, by putting these two over onto the other side of the equation, equal 10. Now this general thing about constraints is, let's say that that's our constraint line there, and we could say put in 10 there and 10 there, and then we can identify a region in there which is, so this region is a feasible set. So we know that we're going to find the optimal value somewhere in there. So the big question is, well, how do we modify these problems where we're just looking at the objective function to take account of the constraints? Well, one straightforward way of doing this is to actually say, well, x2 is equal to 10 minus x1, okay, and then you can substitute that back into the objective function, and you've got rid of the constraints, and you've just got a problem that's in one variable, namely x2. But that soon becomes a very difficult way to solve this problem. So we're not going to use that method, although actually occasionally it is a very useful method to use. When it comes to Mathematica, it's actually really straightforward to solve these problems, and we're doing it here so we know what the values are. So you just say that we put in the objective function there, and then we put in the constraint there. We forget about the non-negativity constraints, just check that the solution satisfies them, and say we're going to maximize over x1 and x2, and you get a solution. So the objective function value is equal to 92, x1 is equal to 8, and x2 is equal to 2. And you notice that those two satisfy the constraints, so we hope we found an optimal solution there. And you'll notice that has a lower objective function value than the unconstrained optimization that we did earlier. That had a value of 108. So that's easy, but doesn't really give us much of an understanding as to what's going on, so I'll make things more complicated. The first thing we need to do is really to define the constraint equation so we can put it into a contour plot diagram, and that's what we're looking at here. So we've got contour plots and we've got arrows indicating the direction of steepest ascent. We have a rather faint yellow point here which gives us the unconstrained solution up there, and then we have the constraint line here, which indicates that we can have 10 of x1 or 10 of x2, or combinations of values for x1 and x2 that sum up to 10, and then we get an optimal solution here which is at 8. And now what characterizes this optimal solution is that in many cases it's what's called a point of tangency between the optimal contour and the constraint line. In other words, those two lines have got the same slope at that point, and you can think about it as right along this constraint line here, and we've got non-negativity, so things can only be positive. Then we have to find a solution to this problem, which is somewhere in this triangle here. And so you can think about moving out in this direction pretty well as far as you can go, and then you're comparing say this contour here. Well, that's got a smaller value than this one, and you're moving in this direction until you get to this point here, and if you keep on moving in that direction, then the level of the objective function is going to be falling away because you're moving to a lower contour. So general rule then for these constrained optimization problems, as long as the objective function is nice and well behaved, and as long as the constraint line is linear or is in this direction, then you're going to find a nice well-behaved optimal solution, which is one of these points of tangency. Okay, so that's what's going on here, and then you can imagine that, let's say you could relax this constraint by shifting the line out, then that's going to increase the objective function value, and in fact that's going to carry on increasing the objective function value until you hit this unrestricted optimal value here. And if you go beyond that, then actually allowing there to be more x1 and x2 and making it a binding constraint, it is actually going to be reducing the objective function value, because you're going beyond the unconstrained optimization. So this is a bit crude, but diagrammatically that's what's going on. Now let's just have a look at how we solve these problems analytically, and how we get out a value for the Lagrange multiplier, which also gives you the value of relaxing the constraint. So this is the Lagrange multiplier trick. So the first thing is to define a Lagrange composite function which includes a Lagrange multiplier for every constraint, and I'm going to have the tradition here of using lambda to represent the Lagrange multipliers, and you can also call these, if you want, slightly incorrectly, but there you go. You can call them shadow prices, and I'll explain why that is a bit later. So a Lagrange composite function includes the objective function, it includes a Lagrange multiplier multiplied by the constraint, and the constraint function is, for instance, minus x1 minus x2 plus 10. Although you can write this in different ways, and it causes a good deal of confusion, but at the end of the day it doesn't really matter. You then take the derivative of the composite function with respect to x1, x2 and lambda 1 and set it equal to 0, and then that in this case gives you three equations in three unknowns, and you can solve that simultaneously, and the Lagrangian multiplier gives you this shadow price of the resource constraint, or of the constraint. It might not necessarily be a resource constraint. So let's set this up as a Mathematica example. So we set this function up here, and that's the constraint function. So we've set it up as minus x1 minus x2 plus 10, and the implication with this constraint is that the constraint is actually that it's equal to 0, but we don't need to put that in, in fact we can't. And then you have the Lagrange composite function, and we've got the objective function value there plus the Lagrange multiplier multiplied by the constraint function. You then use the derivative command, and in the derivative command you have a list of your variables, which are x1, x2 and Lagrange multiplier 1, and then that gives you three partial differentials. So the one with respect to x1, the one with respect to x2, and the one with respect to the Lagrangian multiplier. And actually this one with respect to the Lagrangian multiplier, if you look at it, is actually just your constraint function. So it's telling you absolutely nothing that you don't know. And then we use the solve command. We've got a list of three equations here. We set them all equal to 0. We solve with respect to x1, x2 and the Lagrange multiplier, and we get the solution here, which is that x1 is equal to 8 and x2 is equal to 2 and the Lagrange multiplier is equal to 4. Okay, and if we shuffle back up here, then we see that that is exactly the solution that we got from using nmaximize. So that was really quick and straightforward. This is much more involved, but it does explain how you solve these things. And then the bit of extra information that you get is that the Lagrange multiplier is equal to 4, and what's that saying is that if the constraint is relaxed a small amount, the objective function will increase at a rate of 4 per unit of resource or constraint. Okay, so that's actually a really valuable piece of information in a planning problem where there are lots of constraints with fixed values in them. So this is just to remind you that it can be solved by nmaximize. That completes part 3.